The discovery of Planck's constant was the birth of quantum mechanics, which is physics on a really tiny or quantum scale. Well, where did it come from? Well, it arose from one of the biggest problems faced by physicists in the late 1800s, called the UV catastrophe. And this is where classical physics, the physics of the big stuff, fails to describe the spectrum of a black body. So to put that simply, if we take a black body, which is a perfect absorber and emitter of radiation, and have a look at what wavelengths it's giving off, classical physics understands what's happening at the larger wavelengths in the infrared region, but as we approach the visible and the UV, it's got no idea what's going on. And in fact, it thinks the energy of these wavelengths tends towards infinity, which is just nonsense. In desperation to reproduce this graph, Planck employs a mathematical technique known as quantization, which is where he takes energy and treats it as a discrete variable instead of continuous. So Planck postulates that energy is made up of little packets known as quanta or elements, and energy can only exist in multiples of these packets. So energy can't just take on any value that it wants to, and this is one of the oddities of quantum mechanics. And it leads to the relationship E equals hf, where E is energy, h is Planck's constant, and f is the frequency of the radiation. And we can make multiples of that just by timesing it by n, which is an integer. Now, Planck clearly feels uneasy about the method he's adopting here, as in a letter to his friend Robert Wood, he explains that a solution must be found to the problem at any cost. At that time, he didn't realise what a major breakthrough he was making, but we can now appreciate that this has huge implications for our existence. So this gives rise to all the energy levels in atoms, and in particular that lowest energy level, which prevents an electron from spiralling into the nucleus and allows matter to exist in the way that we know it. Now, dealing with the quantum world, we would expect Planck's constant to be a really, really small number, and it is. Its accepted value is 6.63 times 10 to the minus 34, which is 0.33 zeros 663, so super, super tiny. And we can experimentally measure a value for h using this Planck's constant apparatus. So with this unit, we are going to measure the individual threshold voltages of these LEDs. Now, the threshold voltage is the voltage at which the LED will just begin emitting photons. But before we go further, let's have a look at how an LED works. So an LED is a semiconductor device which has a p-n junction in it. So the n-type region is the cathode and has an excess of electrons in the conduction band, and the p-type region is the anode, and this has these positive electron holes in the valence band. And those two regions are separated by something known as the band gap. Now, when a sufficient voltage is applied, electrons will move from the n-type to the p-type, and energetically they move from the excited state in the conduction band down to the ground state in the valence band, and as they do so, they'll emit a photon. And the voltage at which this begins to happen is known as the threshold voltage. So we can equate the photon energy to the energy of the electron jump. So we get E equals hf equals EV, and then with some substitution and some rearranging, we end up with 1 over lambda equals E over hc times by V. Now, if we compare that equation to the linear line equation, we can see that a graph of 1 over lambda on the y-axis against V on the x is going to give us a gradient of E over hc, and we can use that to determine h. So what does it all mean for this apparatus? Well, you can see there's an array of LEDs on the unit, 5 of which are in the visible region and 2 are in the infrared. And what I'm going to do is I'm going to slowly increase the voltage and determine the point at which each LED comes on. To make my results a bit more accurate, I'm going to use this viewing pipe, which sits securely against the unit, and it blocks out all the ambient light so I can see just the light from the LED. So let's get the equipment set up. So first off, I'm going to provide a supply voltage of 5 volts in the back of the unit. And you can see here that there's sockets for an ammeter. Now, if you want to measure Planck's constant really accurately, it's important that we attach an ammeter across this junction. So that's going to give us the point at which current begins to flow. And although we might not be able to see that using our eyes through this viewing pipe, the ammeter is going to tell us that that's the case. So you can still get pretty good results without using the ammeter. So for the moment, we're just going to patch across there. We are also going to need a voltmeter. So I'm going to attach that over where the symbol tells me to. So I'm going to attach the positive terminal to the top rail and the negative terminal to the bottom rail. I'm going to turn the voltmeter on, And then we can select an LED using this switch here. I'm going to make sure I'm selected on the 464 nanometers on the left. And then what we have to do is just slowly increase the voltage over here just until the LED starts to light. Again, looking through your viewing pipe. So once you've got that threshold voltage on your voltmeter, the point at which the LED only just begins to light, we can write that down in a table of voltage against LED wavelength, and from that we can produce our graph. So using this setup, we can use the first 5 LEDs that are in the visible spectrum. If we want to get our result a bit more accurately, we can use the N2 as well, which are in the infrared. But remember, we're going to need to swap out this yellow cable for an ammeter instead. And that's going to give us the point at which current begins to flow, and we can take the threshold voltage at that point. So now that's all that's left to do is to turn this round, begin collecting my data, and then we can plot our graph. So with this set of results, we've managed to get to within 7% of Planck's constant, which is a really good approximation. But given that we said we're going to try and see how close we can get, we took another set of results using the ammeter instead. And here's the graph. And you can see that we've now managed to get to within 3%, which I think is really quite impressive for a student laboratory setting. For more information, please visit our website, lascells.com.